Okay, today we are going to talk about the dot product of a vector. This is section 6.2. And this is what we get when we multiply two vectors. So far, we've multiplied scalars, aka numbers, times a vector, like this. And I multiply both components. Remember, a scalar is a number, a vector has magnitude and direction. Well, let's draw the one I have up there, actually. And it's, yes, functionally like it's put on a graph. The components here are the magnitude. There's the angle here, gives me the direction. And the magnitude is used the Pythagorean theorem. Let me grab a calculator to do that. Square root of 232. So that's magnitude and direction. When I multiply with a dot product, two vectors, I get a scalar. Okay. This feels a little weird, but that is how it works. So here's the formula. There's also another way of multiplying vectors called cross product. It's a three-dimensional. You end up with a three-dimensional vector. It's a little more complicated. So I can write two vectors. This is going to be vector u. It's got u1 and u2, or ux and uy. And a dot product is indicated with a raised dot, aka the standard multiplying symbol. A cross product would have an X in there. Your elementary school multiplying symbol, but that definitely means cross product. Okay, and this is going to equal, you take your numbers, because remember u1 and u2 are just X components. You multiply your X components and you multiply your Y components and you add them together. That's a dot product. Okay. Let's do an example of one of those, and then we'll talk about some of the rules. This is example 1. So it's 3 times 5 plus 4 times 2. And oops, don't need that parentheses there. As long as you remember what the rule is, this isn't particularly hard. 15 plus 8 is 23. The rule is simply multiply the x's, multiply the y's. So now I've got 1 times -4. Maybe let's do parentheses here. Plus -2 times 3. That's -4 plus -6 is -10. This is written in a little different form. Remember, this is the physics notation, I hat, j hat. If you're looking in the book, it's just a bold I and a bold j. You cannot imply the multiply with these. You have to specify the dot. Again, because the dot product is different than the cross product. So here I've got, again, I don't include the i's and the j's, I just do the components. So it's 2 times 3 plus -1. This j hat here is -1 j hat. times -5. I guess I didn't really need the outside parentheses. It's 6 plus 5 is 11. Okay. So this is a couple of dot products. Okay. So here's a couple of rules on dot products. U dot V is equal to V dot U. We know that's true for regular multiplication. I could show it by showing the parts, and all you're doing is switching the parts inside. Not all multiplication is, the word for this is commutative, meaning I can switch orders. It's true for standard multiplication of real numbers. Next chapter, when we do matrices, it's not true. Okay. But it is true for dot products of vectors. I don't think it's true for cross products. I'd have to verify that, but I believe it's not. I haven't done a lot of cross products in my life. U dot U is, remember the absolute value symbols mean around a vector mean magnitude. So I could probably put these vector arrows above them. Yes, these are all vectors. I'm not going to put them above everything, but you get the idea. The 0 vector times dot any vector, and again, the order doesn't matter here, is the 0 vector. That means 0 in each direction. U dot V plus W. This is just standard distributing. Again, all these laws that we're used to, I need a dot product, both of those. Again, I can't imply the multiply here because there's 2 types of multiply. Or I can switch the order on that. It's also, so that's distributive. It is associative too. Actually, this is not perfectly the same. Is it? No, not exactly. And then, oh, this is the associative. So here we've got a scalar. C is a scalar. So I'm going to actually notate my vectors here. So that's one option. Or it could be you do the dot product first. So it doesn't matter which one you multiply. Okay. I'll show you the proof of number 1 quickly here. So U dot V is equal to U1 times V1 plus U2 times V2. And we know that V dot U is equal to V1 U1 plus V2 U2. And there it is. There. Since these are commutative, this is just regular multiplication of real numbers. These 2 are equal. Not exactly swap, but you can swap them because they're equal. Okay, the angle between vectors. This is pretty useful. Oh, no. Let's use dot product to find length. Let's do example 2, and then I'll do angle between vectors. So use the dot product to find the length of this. The length is essentially the magnitude. So there's a property that says the magnitude of u, and this is essentially just the Pythagorean theorem, but can be done this way. Again, these are vectors. Square root of u dot u. So the magnitude of 4, -3 is equal to the square root of u dot u is 4 times 4 plus -3 times -3. And that's the square root of 16 plus 9 is 25, or 5. And yeah, I could have just done that with the Pythagorean theorem. It's essentially what I did. And that's there. Okay. Now we're going to talk about finding the angle between vectors. And there's this property of dot products that says u dot v over magnitude of u, magnitude of v, is equal to the cosine theta. Which means really I want the angle, so I've got to use the inverse cosine of my whole other side. U dot v over u, magnitude of u, magnitude of v. And again, most of the time I'll abbreviate that without the arrows of the vectors, but just putting them in for now. The proof kind of involves a law of cosines, and I'm not gonna show you the proof unless you really want to see it. I'm guessing most of you are gonna go, proof. No, I don't need to see that. I'm gonna skip through it anyways. So okay, find angle between vectors. Here I've got two vectors. First thing I can do is find the magnitude. And I'm just going to do the Pythagorean theorem way. 2 squared plus 3 squared. 4 plus 9 is 13, square root of 13. This one, 2 squared is 4, -2 squared is still 4. Plus 5 squared is 25, square root of 29. So, again, I'm just going to do the inverse cosine one. Dot product, 2 times -2 plus 3 times 5 over square root of 13, square root of 29. And I just want an answer. We're going to do this in degrees. So I'm going to stick that into my calculator. And yeah, I'm going to do -4 plus 15 is 11. And I get 55.5 degrees. Part B of this gives me two other vectors. Angle brackets around my vectors. Again, magnitude, square root of 5. Square root of 10. So theta equals the inverse cosine of 2 times -1 plus 1 times -3 over square root of 5 times square root of 10. And when I put this in the calculator, I'm doing That's -2, that's -5. With the square roots, I can just multiply what's inside. But the one above, I did just plugged in 13 times 29, so I'll show that. Here, I would probably just make the 5 times 10 of 50. And you don't have to necessarily simplify this, but if you can, it's sometimes a little quicker. 135 degrees. Okay. Orthogonal vectors. I misspelled it. This word orthogonal. Orthogonal means they meet at a 90-degree angle. Now, the thing about vectors is it's easy when they're, you could say they're perpendicular, but they're not really lines. They don't continue in both ways. And they're in 3D space. So you're putting a flat plane, whether that be like going like this, or going like this, or going like this. So orthogonal vectors meet at 90 degrees within a plane. Okay. So vectors are orthogonal. U dot V equals 0. If you want to prove they're orthogonal, you simply do the dot product. So we're going to check two vectors. This is example 4 now. Doing parentheses instead of angle break. Which is not terribly uncommon. I just like the angle braces better. And our book uses angle braces, so I like to take the opportunity to follow it. I like them better, period. Kind of always have. And that's -12 plus 12 does equal 0. These are orthogonal. Okay. A vector projection. Vector projections are a little weird. Okay. And I think I showed you tilting an axis before. This is kind of what vector projections are about doing. So the projection of U onto V. And this is about breaking into components based on the directions off another vector. So I believe I showed you tilting axes, taking your X and Y and tilting them in the last section. That's kind of the idea we're doing here. And we notate this like that. Projection of U onto V, the V is the subscript, equals U dot V over magnitude of V squared times V. That's going to give me a vector. This set of parentheses, dot product is a scalar, the magnitude squared is a scalar. So that's just a scalar times vector V. So I'm going to try to draw this. They've got a vectors U and V, and this is going to be example 5 using this projection. Then we'll use a projection on a thing. I might just tilt the axes instead of using the projection formula. So here we've got a vector, it's X and Y. This one we're going to do with actual projections. So vector u here that we're going to project onto vector v is going to be this 6. Actually, let's change my color. Do this in red. U equals 6, 2. So I'm going to draw that on my graph. And that's right here. That is U. Vector V is equal to -5, -5. I know, 5, -5. Oh, that's going down here. And that's V. The projection, and I'll use the formula and then I'll draw it on there. So I'm going to need here magnitude of V is going to be equal to square root of 50. Again, 5 squared plus 5 squared, 50 square root. So here I've got u dot v. 6 times 5 plus 2 times -5 over square root of 50 squared. It's going to be 50 times the vector v. So this is 20 over 50, which I can reduce to 2/5. And that's going to be 2, -2. Okay. So essentially breaking, so it's saying this blue one essentially is the axis, and it's figuring out which component, how far am I going here along blue with my red one. And this is projection of V on U. Okay, that's my projection. It's how much am I going in that direction? I can look at it like components on there, and here's my other component, and that's a 90-degree angle. That is like components if I'm going components along the blue vector or V, okay? And the projection is only the component in that direction. Okay, example 6, you can do using projections, or we can just do it using my tilted axes way, which is how you do it in physics typically. And I think it's typically easier, so we're gonna go the easy way. So Juan is sitting on a sled on a hill inclined at 45 degrees. The combined weight of Juan and his sled is 140 pounds. What is the force required for Rafaela to keep the sled from sliding down the hill? Okay, we're going to assume Rafaela is holding the entire weight of Juan. And that there is no friction. And the friction between snow and a sled is pretty low, so it's going to be a pretty good approximation. We know that we have here 45 degrees. And gravity, there's a force vector of 140 pounds. That's Juan's weight. And I can make components out of this. The key to this with the components, they must make a right angle with your tilted y-axis. Suppose you could do it to the x-axis. I don't like to. This here, if I keep going, gravity pulls straight down, always straight down towards the center of the Earth. This angle up here, I know that the 45 and the corner here and up here are going to add to 90. So that one also is 45. And here I have a right angle, meaning this is 45. They won't always be exactly the same, but these two will always match. So I can get my two components. How do I get this side? Y, X, cosine of 140, no, cosine of 45 angle is my, angle's what goes in my cosine, is Y over 140. So I multiply both sides by 140, and I get 140 cosine 45 equals Y. And again, we're going to do this in degrees because well, I gave you the angle in degrees. You better do it in degrees. Y is 98.99. The X is going to be the same thing, but with sine. And yes, this is a 45, 45, 90 right triangle. It's the same. I don't need to plug it into my calculator. Okay. And in order for something to be stationary, the forces in physics, and this is in life too, but the forces must sum to zero in each direction. I'm going to take the y forces based on my tilted y. The ground is holding him perpendicular to the ground with what's called the normal force of 98.9. Again, if you don't know that, if you're not in physics, you don't actually have to know that. But the X force also, and this is, I'm going to call this force Raphael, because she's the one holding it. So we're going to call it force R. So I've got 98.99 pulling down the hill with gravity. Is gravity really pulling? No, it's pulling straight down, but down the hill is the closest thing it can get to straight down because the ground won't let it go straight down. Rafaela's force must be equal to that to hold one in place and keep it from going down the hill. At some point, hopefully she'll let go of it and it'll be good. So she's got to hold roughly 99 pounds. Hopefully she can do that. Okay. Work. Now, according to physics, work is the force times the distance that something travels times the angle between the force and the direction of motion. Sometimes you'll have this cart here and you'll be pulling with a rope kind of up like that. Well, the cart is going to stay on the ground. This is going to be the angle between them. There's a way to do this with vectors, though. Distance can be, well, distance is vector AB is what they're doing. And that when we say AB, we're saying it goes from point A here, travels to point B there. Actually, let's change the color on that. My cart travels from point A. So the vector is the motion vector. You can also write it like this: force times magnitude of AB times cosine theta, which is my general form up here. So, and we talk about work done on an object. So technically, if an object is not moving, No work is being done on it, okay? We don't talk about the work you do, we talk about the work done on objects. Or potentially the work done on you as you get pushed or pulled or whatever. So find the work done on a 10-pound force acting in the direction of 1, 2, moving an object 3 feet. So these are my points A and B. It's moving it horizontally 3 feet. So this here is a dot product, okay? No, this is a magnitude, okay? So I can just do this with the dot product of my two vectors method, and I don't have to worry about the angle. So AB is simply a vector, goes from 0, from 3. So work is equal to the force vector, 1, 2, dot the motion vector, which equals 1 times 3 plus 2 times 0 equals 3 foot-pounds. So maybe I can spell pounds and not try to mix the abbreviation of the word. So foot-pounds is basically a foot times a pound. And I shouldn't have a dash, it should have a hyphen. That's different than foot-pounds of torque. It means something different, even though it's the same pronunciation. In the metric system, we call it joules and newton meters. They actually have different units, even though the joule is a newton times a meter. We call it joules for energy. And that's work. Use the dot product. It saves you having to find the angle. Okay, that is section 6.2, dot products.